All right, why does constant rate of change mean the graph is linear? So we've kind of been taking it as an assumption, right? Because we all know, like, a constant slope means the thing is linear. But we also need to have an understanding of why that is. And it has something very specific to do with the coordinate plane. Because if you, how many people have learned at some point about polar coordinates? Raise your hand. So will a constant rate of change be straight on a polar coordinate frame? No, right? It goes around in circles. So why is it linear on a Cartesian coordinate system? So what I first want you guys to do is to, can you please draw two graphs? This is really bad. All right, the first one, you're going to draw a line. And on the second one, I want you to draw something nonlinear. So if everyone can go ahead and do that, something nonlinear. I'm going to go. There we go. And then in your groups, I want you guys to draw three dx and dy pairs. So start from anywhere on the line, draw the dx, draw the associated dy, the little bars. Do that 3 times over here, do that 3 times over here, and try to answer the question, why is it that a constant rate of change means it must be linear? It's actually a trick only of the Cartesian coordinate system, the squarish grid. But we should have an understanding of why that is. We shouldn't look at a line and say, oh, constant rate of change, because my teacher told me, right? There should be a specific reason. So we're going to go over that reason.
We're doing this on GC?
You can do that on paper because it's much easier to draw this on paper. GC will come a little bit later. And yeah, talk to each other. Scooch into groups. Scooch, scooch. Scooch, scooch. I'm going to come around to look to see for those pairs. It should almost look like a triangle, right? Almost. Right, so draw them. Draw a little dx on the graph and then draw the what goes with that, and it almost looks like a triangle. Well, on the line it'll look like a triangle, and there it'll look like a curvy triangle. The third side will be curvy. Exactly. Oh, so that's excellent. What will a dx look like? A dx? If I had to draw it? A little horizontal line that changes away from one of the situations? Exactly, not just 2 and 3 image. Then,
The ratio is probably the same, but, well, it is the same, but.
2. See the red and blue very well, but I tried to make the dx's red and the dy's blue. So if you have 3 of these, now think about them as triangles. So on the line, they're actually triangles, right? Over here, though, they're kind of triangles. So let's kind of make them triangles. Yeah. What is it about the changes of the line that make it constant rate of change and therefore mean it has to be linear, like it didn't have any other choice but to be linear? What we want is an answer to the question from now on when we see a straight line, if someone says, oh, that's a constant rate of change, or if we say that's a constant rate of change and someone says, how can you assume that? We want an answer to that. Does anyone have any ideas?
Just going out on a limb, is it because linear lines are tangent to themselves?
That is actually getting quite close. Tell me more about what you mean.
Well, when you turn the triangles on the one on the right, you turn it into triangles, but make the straight lines. I guess kind of made tangent lines to it.
Okay.
I guess that's the concept that it's going towards. So you can't do that with a straight line because the entire line is tangent to itself.
So can you talk more about, can you actually, hold on for 1 second, can someone expand on that, talking specifically about the changes in x and the changes in y that you drew? What about those force the graph to be linear? And again, you don't have to have an automatic right answer, but pass something out. Leslie?
Because the changes in y and changes in x is the same ratio throughout the entire function.
It has to do with that ratio. That ratio is the constant rate of change, right? But that ratio is also something else. So the hint comes in this ratio. So the dy dx ratio is the constant rate of change, but it also, this ratio, also tells us something else. Oops, come on. It also tells us something else. And that something else is why on the Cartesian coordinate plane, the graph must be linear. I'm going to give you guys a couple more minutes to try to discuss. And again, we already know the ratio gives us the constant rate of change. It tells us something else, though. Go. What else does the ratio of those two sides tell you? Think back to previous classes. That's all right. That's why, it is an open discussion. But there's something else that ratio will tell you. So I'm not going to say like, oh yeah, we did a lot of that. Alright, I'm going to do my best. Come on. I'm going to clear this, okay, and redraw part of it. Keep talking. I can read.
I know how.
That's horrible drawing, but I hope you guys can understand. Okay, and so dy, dy over dx tells us the ratio of this side to this side, right? This side to this side, this side to this side. It is constant over here. It is non-constant over here. So when it is constant, what about these triangles say it has to go in a straight line? And it has to do with the class that you took right before this. No. It has to do with trigger pre-calc. What makes this dy dx? Look at it now as a physical object for a second. What must remain constant? Why? What does dy over, if this is dy, guys. This is dy, right? And this is dx, okay? If it's constant, then what else is constant? Not the 90 degree. What in trig involves this side and this side?
Is it the hypotenuse?
It's not the hypotenuse because it's not the length of it. We want to figure out what keeps it going. When something's going linear, that means it's going at the same slantiness, right? And what measures kind of like the slantiness of a physical object? The degree. And what is constant if this side divided by this side is constant? What else is that? What's that side divided by that side? Tangent. Right? If dy over dx is constant, therefore, tan theta is constant. And if tan theta is always the same thing, guys, if I keep calculating tan theta for my first triangle and for my second triangle, for my third triangle, and tan theta is always the same number, then what can I conclude? If tan theta is always constant, then still think about the triangles. What about the triangles? The angle, right? If I go tan theta is always the same thing, doesn't theta always have to be the same thing? Right? If tan theta is constant, then theta is constant. All right, so right here, this theta is equal to this theta is equal to this theta. And so they have the same slantiness, and so it has to keep going up at a line. This guy keeps having different values of tangent, right? Look at the ratio of this to this. This will be, tangent of theta is going to be one thing, another thing, another thing. That's why these angles change, and so that's why it moves in a nonlinear way. Okay? There's a reason for every single thing that we assume. We do not have time to do the GC thing, but do I have a couple more minutes? No, I don't. All right. Today, 2 review sessions. They are in the same place where the test will be. There is no new homework. The homework is to finish the homework, online homework. And yes. You want to come on up and talk? Yeah.